want to go over some times or some instances where limits don't exist. I'm going to come up with 3 examples to illustrate that. So, first example we're going to look at is a limit as x approaches 0 of the absolute value of x over x. Okay, so if we just plugged in, we would get 0 over 0, which is an indeterminate. So now we're going to look a little deeper. We're going to dive in a little deeper. Let's consider that the absolute value of x equals positive x when x is greater than or equal to 0, and negative x when x is less than 0. Okay, so if we have this, then the absolute value of x over x equals x over x is 1 when x is greater than or equal to 0, and negative x over x is negative 1 when x is less than 0. So we got that the absolute value of x over x equals 1 when x is greater than or equal to 0, and negative 1 when x is less than 0. So what does that look like on a graph? Let's see, I'll draw it up here. Alright, so we got from the right of 0, we have 1. So I'm going to put a 1 here and a negative 1 here. We just have the graph of 1, straight horizontal line. And a dot here because it's greater than or equal to, so we have a closed dot here. We got that. The second part of our graph is negative 1 if x is less than 0. So to the left of 0, we have an open dot because x is less than 0. We have an open dot and a line to the right of 0. So if we were to take the limit as x approaches 0 from the left, we would get negative 1. That looks like this. The limit as x approaches 0 from the left. Anytime you see a minus sign there next to that number, you're approaching that number from the left. So we would get negative 1 if we were approaching 0 from the right using this plus sign. From the right, approaching 0 from the right, we would get to 1. And as you can see, negative 1 does not equal 1. So this limit doesn't exist. Okay, so this limit doesn't exist, and you call it a jump discontinuity because we have this jump from negative 1 up to 0. So we're going to just put does not exist. Okay, so let me do another example. Alright. Next example. Limit as x approaches 0 of 1 over x squared. Okay, so let's try to plug it in. We get 1 over 0. Another indeterminate form. So with this particular indeterminate form, we can say that the limit equals infinity. Anytime you have a number over 0 as your limit, you can say that it's plus or minus infinity depending on whether you're approaching 0 from the right or the left. If you're approaching any number, not just 0, if you're approaching any number from the left, you're going to have a negative infinity in this case. If you're approaching any number from the right, and you have this case, you're going to have a positive infinity. So, let's see, we're going to draw it out. Okay, so for this particular function, we have a horizontal asymptote at 0. And we also have a vertical asymptote at 0 because when you plug 0 in for x, you get 0 in the denominator, it's indeterminate. So we have a vertical asymptote here too. So our graph is going to look like this. And as you can see, as you approach 0 from the left and the right, you approach infinity, which means your graph is going to keep going up an infinite amount of times, which means the limit never approaches a real number or a real defined number. So again, we're going to put does not exist. And sometimes on tests, you'll find that your teacher will either want you to put this as the answer or actually specify that it's infinity. It's going to be in the directions. But usually when you get infinity, that means your limit does not exist. All right. Last example. All right. Let's take the limit as x approaches infinity as a bad infinity sign. Infinity of cosine of pi of x, pi times x. Alright, so if we plug in, we get cosine of infinity, which is indeterminate. There's no point in going over that. So I'm going to go ahead and set up a table, just like we did with estimating. So we got x and f of x. And I'm going to plug in, I'm going to start with 0, 1, 2, 3. Okay, so plugging in 0, I get cosine of 0, 0 times pi is 0. Cosine of 0 is 1. 1 times pi is pi. Cosine of pi is negative 1. Plugging in 2 pi. Cosine of 2 pi is 1. 3 pi. Cosine of 3 pi is negative 1. So, as we approach infinity, our graph keeps jumping from 1 to negative 1 and back. And it's going to do this an infinite amount of times. So this limit doesn't exist because your graph looks like this. Negative 1, 1. At 0, it's 1. At 1, it's negative 1. At 2, it's 1. So your graph is going to keep going like this. So as you approach infinity, your graph is going to jump back and forth, which means the limit doesn't exist. This form is this is what you call oscillating behavior. So again, this limit does not exist. Alright, so I'm going to write down some guidelines on why limits don't exist real quick, just to recap. So three cases. Three cases your limit doesn't exist. One, the two one-sided limits don't equal each other. So if you have this, you have that limit as x approaches 0 from the left of f of x does not equal the limit as x approaches c from the right of f of x. So if the two one-sided limits don't equal each other, your limit doesn't exist. Another case, the limit as x approaches c of f of x equals plus or minus infinity. Again, if you have infinity, your limit doesn't exist. And the last case is if the limit as x approaches infinity of f of x is similar to the limit of x, the limit as x approaches infinity of something like this. -1, this is x. For some number a. In other words, if your function oscillates between two different numbers, your limit doesn't exist.